Welcome, curious listener, to the deep dive. Today, we're plunging into, well, the very fabric of reality, the absolute fundamental building blocks of the universe. Our mission is to unpack what these tiny entities are, the elementary particles, and meet the key players that make up, well, everything around us.
It's a great topic because, once upon a time, we really thought the atom was it. The smallest thing. I mean, the name atom itself comes from ancient Greek atomos, meaning uncuttable, but science had other plans, didn't it?
It certainly did, and that's really the core idea, isn't it? How our whole definition of indivisible has just radically changed. This quest for the ultimate building blocks, it really got going with discoveries like J.J. Thomson finding the electron back in 1897,
Right.
then Rutherford finding the proton, Chadwick the neutron. And for a while, people thought, okay, these are the basics.
Exactly. But what's so fascinating is how that understanding kept evolving. We later found out protons and neutrons, they aren't elementary at all. No, they're actually made of something even smaller. And, well, that's where the standard model of particle physics comes in. It's our current best map, really.
Okay, the standard model, our guide to the really small stuff. So it recognizes 17 distinct elementary particles, and they fall into two main families.
That's right. You've got the fermions, which build matter, and the bosons, which carry forces.
Got it. Fermions are the matter builders.
Yeah, they're literally the stuff of the universe. They have this property called spin, kind of an intrinsic angular momentum, and they obey something called the Pauli exclusion principle.
Pauli exclusion. Sounds complicated.
Well, it basically just means two identical fermions can't be in the exact same quantum spot at the same time. And this rule, it seems abstract, but it's why matter takes up space. It's why atoms are stable and don't just collapse. It's fundamental.
Wow. Okay, that is profound. So let's dig into these fermions then. You said 12 types.
12 types, yeah. First up, the quarks. There are 6 flavors. Up, down, charm, strange, top, and bottom.
And this is where it gets really weird, right? Quarks.
Oh, yeah. Get this. They carry fractional electric charges, like plus 2/3 or minus 1/3. We never see that charge floating around on its own. And they also have this color charge. Nothing to do with actual color. It's a quantum property. Think of it like a super strong charge.
A strong charge. It's why you can't find a quark by itself.
Exactly. They're always glued together inside bigger particles called hadrons, like protons and neutrons. You've just never seen an isolated quark. It's quite bizarre.
Okay, mine's slightly bent. What's the other group of fermions?
The leptons. Also 6 types. The electron we already mentioned, then the muon, the tau, and each of those has a corresponding neutrino. So 3 charged leptons, 3 neutrinos.
And unlike quarks, these don't feel that strong color force.
Correct.
Yeah.
Leptons are immune to the strong force. The electron is a perfect example. It really is elementary as far as we know.
And you mentioned antimatter. Each fermion has a twin.
Yep, an antiparticle. Like the positron, it's the electron's antimatter twin. Same mass, opposite charge.
Okay, so fermions are the matter. But how do they talk to each other? How do forces work? That must be the bosons, right? The communicators.
Precisely. Bosons mediate the fundamental forces. They have integer spin, and unlike fermions, lots of bosons can be in the same quantum state.
So who are the players here?
Well, you have the gauge bosons. There's the photon massless, carries the electromagnetic force. That's light.
Light itself, wow.
Then there are 8 kinds of gluons. They carry the strong force, the one that glues quarks together inside protons and neutrons. Super strong, hence the name gluon.
Gluons, got it. And the weak force.
That's mediated by the W and Z bosons. They're quite heavy, actually, and responsible for things like radioactive decay.
Okay. Photon, gluons, W and Z, is that it for bosons?
Almost. Then there's the real celebrity of the particle world, the Higgs boson.
Ah, the Higgs. Found relatively recently, 2012, wasn't it? And it's responsible for mass.
That's the idea. It gives other particles their mass through the Higgs mechanism. Imagine this invisible field, the Higgs field, permeating space. Particles interacting with this field gain inertia, which we perceive as mass. More interaction, more mass.
So without the Higgs field, or the Higgs boson, nothing would have mass. We wouldn't exist.
Essentially, yeah. Everything might just be massless, zipping around at the speed of light. A very different universe.
That's incredible. And wasn't there one more?
Yeah.
Something hypothetical?
Ah, yes, the graviton. It's theorized to carry the gravitational force, but we haven't detected it yet. It's a big missing piece in linking gravity with the standard model.
So bringing this all back to you, our listener, why does this matter? I mean, these particles are unimaginably tiny.
Because this model, the standard model, it explains almost everything we observe.
Right. The light from the sun, the chemistry holding your body together, the nuclear reactions, it all comes down to these particles and forces.
Yeah.
It's the blueprint for reality.
It is incredibly successful, but, and this is important, it's not the final word.
Right, you mentioned gravity isn't fully included.
Exactly. And it doesn't explain things like dark matter or dark energy, which make up most of the universe. We know they're out there, but they don't fit neatly into the standard model.
So the deep dive continues, really. The adventure isn't over. There are theories like supersymmetry, string theory, suggesting even more particles, maybe more dimensions.
Who knows what we'll find next?
So for you, the learner, think about this. Our idea of indivisible shifted from atoms to protons and neutrons, then down to quarks and leptons. What other layers might be underneath? What happens when we push energies even higher? It really makes you wonder what's next, doesn't it?